welcome to this particular lecture. Now, in this lecture we will look at electronic module or signal conditioning circuit for gas sensor. Now, when you talk about sensors, there are several kind of sensors. So, starting from thermal sensors, right, we have pressure sensors, force sensors, then we have piezoresistive sensors for strain gauge. We have VOC sensors, which stands for volatile organic compounds. We have gas sensors, right, and so on and so forth. There are a lot of other sensors as well that I have not talked about, but there is a slide which will explain variety of sensors available in market, and from those sensors we will pick one which is the gas sensor. We will understand what kind of gas sensors are available, we will understand what is the principle behind the gas sensor, and then we will see how can we design an electronic conditioning circuit for that particular sensor. Now, when I am talking about gas sensor, if you think from engineering point of view or from the industry point of view, in fact, then you can use this sensor for sensing CO2, right, which is a leakage in a industry, or you can use the sensor for understanding the leakage in a pipeline, which is a chemical pipeline, and there is a importance of measuring that particular leakage in an industry. Now, when you talk from medical point of view, if I have a group of sensors, I can delineate a particular volatile organic compound from the breath, and that is called studying the breath signature of a patient. For example, if a patient is suffering from a particular disease, the some of the volatile organic compounds will be in higher concentration compared to other VOCs. So, if a person is suffering from ketosis, which is a diabetes, then our breath has several kind of VOCs along with gas. The VOC stands for volatile organic compounds, like I said. For example, we are using petrol, diesel, right. Now, I do not say we exhale VOCs which are similar to petrol, diesel. I am just giving an example of volatile organic compounds. So, if you drop a petrol on the table, it will evaporate. Same way, you drop a diesel on the table, it will evaporate. Drop acetone on the table, it will evaporate. Drop ethanol on a table, it will evaporate. All things which are volatile in nature at room temperature are called volatile organic compounds. So, what I said is that we exhale several VOCs like acetone, methanol, IPA, and similar kind of VOCs along with CO2 and humidity in our breath. Now, if a person is suffering from particular disease, certain VOCs are of higher concentration compared to remaining VOCs. If you can detect or if you can delineate those VOCs from the breath, then what you can say, you have developed a non-invasive way of measuring disease. Now, the point that I am making is that if it is a cancer, then also you can detect a certain VOCs in higher concentration compared to a person who is normal, and if you check the breath signature of the person suffering from cancer and person who is normal. So, the point here is that if I can design and fabricate a sensor and I can use those sensor or one or array of sensor along with electronic conditioning circuit, then I can understand what is going on and how can I see the change in resistance corresponding to the particular VOC. So, if it is a resistive sensor, when you expose the sensor to a gas, the resistance would change. That resistance we need to convert to a readable format. For changing from the change in resistance to a readable format, what we need to use? We have to design the signal conditioning circuit. Now, we will be talking about metal oxide gas sensor. So, when you talk about metal oxide gas sensor, this is a conventional sensor construction where you can see a ceramic tube, and the ceramic tube has a sintered SNO2. What does SNO2 stands for? SNO2 stands for tin oxide, alright, and then there are electrodes. So, let me first show you few of the sensors and then we talk about the sensor construction, it will be kind of easier if I want to show you the sensor, I have brought few of the sensors which we have bought from Taguchi. Taguchi is a company in Japan. So, if I show you the first sensor if you can see, it has a 4 different terminals as you can see in my hand, and this 4 terminals is having and in the front there is a mesh, it is a there is a cover. There is a role of having 4 terminals and a cover. So, we will see what is the role. I will open the second sensor. So, you will understand and actually I will show it to you few of the sensors. This is the second sensor, again you can see here there are 4 different pins which you can see, and in the front there is a mesh, right, there is a mesh in the front, and if you see there are 4 different terminals which are here. Now, there is a role of these 4 different terminals, and I will show it to you in the slides what each terminal role is there, alright. Same way, if I show you another sensor, I can show it to you right over here, right, and here what you see is again there is a casing on the top and there are 4 terminals in the bottom. Again, what is the role of these 4 terminals, we will check in the next slide, right, and each sensor is meant for a particular application. Now, let me show you a sensor with a kind of signal conditioning circuit. So, now I am holding a CO2 sensor which is right over here. So, if you see the CO2 sensor, yes, and on the back side there is a whole signal conditioning circuit which you can see here, right. So, this comes with a signal conditioning circuit, but if I talk about other sensors, they do not come with signal conditioning circuits. For example, if I am showing it to you the earlier sensors that I have shown, they do not come with signal conditioning circuits, these 3 sensors, right, all 3 sensors they do not have any signal conditioning circuit, but this one has its own signal conditioning circuit which is on the back side, this is the front side, right. So, it is kind of very easy to understand, easy to see how the sensor looks like. Similar sensor, if I want to design a signal conditioning circuit using Arduino or using Raspberry Pi 3, what kind of circuit we can design, we will see in the slides. Now, if you focus on the slide, what we see is there is a sintered SNO2. SNO2 stands for tin oxide, right. Now, there are lead wires. So, let me write down or give the number to each of the wire. So, lead wire 1, lead wire 2, heater coil is 3, 1 here, and the second end of coil is given number 4. Now, you can correlate why we have 4 different terminals at the back side of the sensor, or 4 different pins for each sensor. The 2 pins, pin number 3 and 4 are meant for heater, while pin number 1 and 2 are meant for electrodes, all right. So, we have 4, that is why each of those sensor were having 4 different terminals. Now, there is a ceramic tube, and within the ceramic tube there is a sintered tin oxide. Why it is called metal oxide? Because you see this is tin, this is indium, this is zinc, this is tungsten. If I want to have metal oxide, then I will have tin oxide, indium oxide, zinc oxide, tungsten oxide, all right. So, this is how the metal oxide semiconductors uses sensing material. They use we have to use a metal oxide semiconductor as a sensing material in the sensor, while you require a heater to increase the sensitivity. You will see why heater and how heater can help in increasing the sensitivity in few slides. For now, this is a conventional way of fabricating a sensor. If I see a second way of fabricating a sensor, it is using a thick film technology. Now, if you know integrated circuit technology, right, then you will understand that there are several kind of technologies. One is thin film technology and another one is thick film technology. In thick film technology, we use screen printing, right. So, using this screen printing technology, using the thick film technology, we have fabricated a sensor, and that is why it is called thick film technology. Now, again the front side of the sensor, right. If you take a substrate can be silicon, substrate can be silicon dioxide, substrate can be alumina, right. Substrate can be polymer also. So, if I take this substrate, this is a substrate, right, and this is the substrate front side, this is substrate back side, then if I have a electrode, right, like this, and on that electrode if I use a sensing material which is my metal oxide semiconductor, right, on the back side I have a heater. On the back side I have a heater. This is the back side, this is the front side. Okay. So, now what is the advantage of screen printing is that we can have high throughput, we can fabricate lot of sensors very quickly, right. The disadvantage is that we cannot miniaturize it beyond a certain point, we cannot make it tiny, all right. So, that is a disadvantage. Again, after you do the screen printing, you have to sinter the material, you have to heat or anneal the semiconductor metal oxide or metal oxide semiconductor to certain temperature, so as to form the sensing layer. This is an example of the type D1, right, which is model 2G TGS 26XX, which is again from Taguchi. And then let us see the circuit, electronic circuit or conditioning circuit for using these sensors. So, the first thing is we have to apply a voltage, we will apply a 24 volts AC or DC, which is your voltage across the semiconductor, and then we have a heater voltage which is your 5 volts, and then finally you have a load resistor which is variable in nature, all right, and the power consumption should be less than 15 milliwatt. If I go for the related equations, then this is how the equations are placed, where we have R equals to V c by V out minus 1 into R L equals to rho by L by A. Rho L by A is nothing but the resistance and rho is your resistivity, L is your length, and A is the cross sectional area. If you increase the length, the resistance will increase. If you decrease the area, resistance will increase. If you increase the resistivity, resistance will increase. If you decrease the resistivity, resistance will decrease. You cannot change the resistivity if you are using the same material, but you can always change the length, you can always change the area. Thus, the resistance is depending on length and area, and it also depends on resistivity, but for the single metal you cannot change the resistivity. So, depending on what kind of resistance you want for a final heater, you need to select that particular material or a metal for fabricating that particular heater. So, if you see the slide, the L is equals to the distance of electrode, A is cross sectional area of sensing layer, rho is specific resistance of the sensor, then we have specific conductivity, we have mu mobility, we have N concentration of charge carriers, and finally Q is a charge of the charge carriers. So, at a constant temperature we have mu constant, that means R changes due to change of concentration of the charge carriers and by gas reactions. So, if I talk about the working principle, what happens is, if I just zoom it out, this gas the sensing material is consisted of several grains, we call grains, GRAINS. Okay. And each grain will lose some electron and will cause a depletion layer, a depletion boundary around it. By losing some electron, it will have a depletion boundary around it, right, in presence of the oxygen in air, all right. And this causes this depletion layer that I have drawn across the brain will cause some kind of resistance value, which we call as a base resistor. Now, if I inject a oxidizing gas. So, there are two types of gases, oxidizing and reducing. If I use oxidizing gas, then the electrons will be depleted further from the depletion layer, and the resistance of the sensing layer would increase. while if I use a reducing gas, then the electrons will be donated and the depletion layer width will reduce, causing the resistance of the sensing layer to decrease. Alright. So, based on what kind of gas we are using, whether it is oxidizing gas or reducing gas, we will see the change in the resistance. This initial is a base resistance or sensor base resistance. This is sensing resistance, which is different than the base resistance. Either this resistance would decrease or it would increase, right. So, that is what is a basic principle behind the gas sensor or metal oxide gas sensor in particular. Same thing is shown here, that in the presence of oxygen there is a creation of depletion layer. If you have a combustible gases like CO2, then the depletion layer would increase and resistance would increase. So, the question is why we have to use metal oxide semiconductor gas sensors. This is because of the volume defect. SNO2 is not stoichiometry in air, but defect structure SNO2 minus this one, right, shows the oxygen vacancy defects. So, that is why we can use the SNO2. Same way, if you are talking about the operating principle, like I discussed, each is consists of a few grains and there is a depletion layer, which is a space charge layer that is created in presence of oxygen, and on inducing oxidized gas or a reducing gas, this depletion layer width will change. So, if I talk about just CO2, then you can see here that my energy band diagram also changes with respect to the reaction of the CO2 onto the semiconductor oxide, and here you can see that O2 minus adsorption consumption by reaction with oxidizable gas molecules, how the energy band diagram changes, where if I talk about the SNO2, then this is how reaction occurs, that with SNO2 if there is a the sensing material is of SNO2, and if I use CO2 as a gas to be sensed, then this is the reaction that is involved. So, oxygen surface reaction is the porous metal oxide sensitive layer, surface gas reaction with adsorbed O2 minus states, and the reaction occurs as 2CO plus O2 minus gives 2CO2 plus electron. Again you can see that we have CH3 CH2OH plus 3O2. So, CH3 3H2OH is nothing but your ethanol, and if you have that, then again you have electron that is released, you have NO2 electron is released, it is absorbed, while you have H2O, then you have electron which is released. So, when there is a electron is released, what happens is that the electron is released into the material, the depletion layer would reduce, and that depletion layer, reducing of depletion layer will cause change in the resistance, which is the reduced resistance. So, you understand by this, if the electrons are donated, then what will happen? Resistance reduces, right, but if the electrons are taken up from the material, resistance would decrease. This is what is there. Now, we need to know why we have to use signal conditioning circuit if we have such kind of sensors, right. And then I will show it to you one example, where I will show it to you how the process flow for fabricating such kind of sensor can be designed, alright, so that you know that in your laboratory can you design such kind of sensors as well or not. So, if I see why signal conditioning circuit is required, then first is we are talking about MQ7, and MQ7 stands for gas sensor. So, if you see MQ7 gas sensor data sheet, the heater voltage has to be provided with high and low values for 60 seconds and 90 seconds as shown in figure below. Now, before we go here, let me just talk one more thing which I forgot. If I see this particular thing, what happens, that when you heat the material, when you heat the semiconducting oxide material, you have a higher sensitivity, because the depletion layer also increases and you have more available sites for the gas to react. At a lower temperature you have these sites which are reduced, but at a higher temperature you have a increase in the reaction sites. So, the gas molecules can react better at a higher temperature compared to a lower temperature. Now, the absorption and adsorption will also be different at a different temperature. Also, if I use the sensor at different temperature, I can also use the sensor as selective sensor. You see, all the sensors, any sensor that I have shown you would be sensitive to one or different gas. Is it selective? That is very important. But when you operate and when you use the sensor, you will find that these sensors are not selective. To make those sensors selective, we need to change the temperature. That is one way of increasing selectivity. Second way of increasing selectivity is by using the sensor in array, and then you use machine learning technique, or you can say artificial neural network, to delineate that particular VOC. So, the role of heater is to increase the temperature of the semiconducting oxide, and by increasing the temperature of semiconducting oxide, you are increasing the sensitivity of the sensor. Alright. So, coming back to the slide, the role of signal conditioning circuit. So, the heater has to provide a high and low values at 60 and 90 seconds, as you can see from here, right, and then what will happen, the sensor has to run with alternating high and low heating cycles in order to provide proper measurements. The operating heater voltage are 5 volts, which you can see. Now, you can see here we require from 1.4 volts to 5 volts. Okay. So, that is why you need to have a signal that you can convert from 0 to 1.4 and maximum phi remains 5. So, we will see how we can design this, but anyway, the operating voltages are 5 volts during high cycle, while it is 1.4 volts while low cycle. So, during low temperature phase, CO is absorbed on the plate, producing meaningful data, but during the high temperature phase, CO is adsorbed. Adsorb is it will come out, adsorption. Absorb is it will be absorbed in the sensing layer, it will have reaction with the molecules, okay, and other compounds evaporate from the sensor plate, cleaning it for the next measurement. That means that whenever we apply 1.4 volts, there will be absorption, change in sensitivity, change in resistance, not sensitivity, change in resistance, and when we apply 5 volts, the gases that were absorbed would be adsorbed. All right. So, the operation is as follows: apply 5 volts for 60 seconds, do not use these readings for CO measurement, apply 144 for 90, use these readings for CO measurement. Go to step 1 and do and follow the step. Conventional analog function generator can produce a signal from 0 to 5 volts. Hence, it is required that we design a signal conditioning circuit to convert this 0 to 5 volts from function generator to 1.4 volts to 5 volts for the output signal. And if you can see the block diagram, the block diagram is that there is a signal generator, there is a scaling circuit, driver circuit, and finally you can see the this is a sensor that we are using. Although the implemented scaling circuit convert the input signal, op amps cannot provide the required power to run the heater unless it is a power op amp. There is another disadvantage, that until we use a power op amp, it can not be used to run the heater or drive the heater. Therefore, sorry for the mistake in the spelling, therefore, it is necessary to have a driver circuit to provide enough current to drive the sensor. One way is by using NPN transistor, as we have seen in the earlier experiments and we will see in the later experiments as well, or by using a MOSFET. So, how can we design the circuit and what kind of equations we need to follow. So, you see, for mapping X from AB to CD, that is from 0 to 5 volts, we to convert to 1.4 to 5 volts. What we require? We require X dash should be equals to X minus A D minus C divided by B minus A plus C. So, this should be 3.65 X plus 1.4. If X is 0, then we will have output as 1.4 volts, right. If X is 1, then we have output close to 5 volts, right. So, the equation of conversion from 0 to 1.4, a gain of 3.6 by 5 must be multiplied with input voltage and voltage of 1.4 to be added as intercept. Indicates that operation amplifier must be having a gain of 3.6 by 5. It is very easy to understand, and an input voltage of 1.4 volts is to be added. This is implemented in the next figure, which is right over here. Right. So, this figure if you see, and you can use a multisim to understand whether the circuit can work according to what we are looking in the theory class. Then what we have is that the gain related equations for the op amp is as follows. For the inverting, R1 by R2 is 3.6 by 5. So, R2 equals to 4.6 kilo ohm and R1 can be 3.3 kilo ohms, right. So, if I use this particular circuit, then if I have R2 equals to 4.6 and R3 equals to 3.3, then only I can have my gain of 3.6 by 5, right. So, a voltage 1.4 is added to the first op amp. If you again see, what we have done is we have added 1.4 volts to the first operation amplifier from the two operation amplifiers shown in the figure, and as the first op amp is used in inverting mode, the output from the op amp is negative. For conversion, a second op amp is used in inverting mode with a gain of 1. So, if you see this one, this op amp has a gain of 1, and it is just to convert the input signal which is out of phase to in phase. So, there is a at the output there is the phase would be shifted because of the inverting op amp, and here again if you use inverting op amp, the phase will be shifted, which is similar to phase at the input signal. So, that is the reason of using a two stage operation amplifier. Again this can act as a buffer or unity gain amplifier because the gain is 1, right. So, using second op amp, we have inverting input R 1 by R 2 equals to 3. So, inverting input, you already know, for inverting amplifier our gain would be equals to minus R f by R I, right. That is why we just consider R 1 by R 2. If I have both the resistance values same, which is 3.3 kilo ohm, what will happen? I have gain of 1. So, if I have gain of if I have values 3.3 kilo ohm and 4.6 kilo ohm for op amp 1 and 3.3 kilo ohm for op amp for R 1 and R 2 for op amp 2, then I can design my signal conditioning circuit, right, and this circuit can be used to convert the input voltage from 0 to 5 volts to 1.4 to 5 volts. Alright, so till then you take care. I will see you in the next class.